In the chemical bonding chapter, we learnt on the first day that we have to understand some theories. Among them, the first theory was Kossel-Levy's theory. In our previous classes, we understood what is meant by Kossel-Levy's theory. In that, many subtopics we discussed, which includes resonance and the polarity of bonds. Now, our next theory is the VESCPR theory, valence shell electron pair repulsion theory. So today's topic of discussion is the same, that is the second theory of chemical bonding, that is known as the VESCPR theory. So my dear students, I welcome you all for the today's session on the VESCPR theory, valence shell electron pair repulsion theory. It is nothing but it is a geometry of a molecule, or known as the molecular geometry. Okay, the molecule takes what type of geometry, what type of shape in space, that is explained by this theory. The meaning is there in the title itself. So first we have to think of in an atom valence shell, outermost shell. In that, how many electron pairs are there? One pair equal to 2, no? That means whether 2 are there or 4 are there or only 1 is there, no pair at all. So we have to understand, we have to take the account of how many electrons are there in the valence shell. Then whenever they go for the combinations, how much they repel, because repulsions are there. Even after the bonding, repulsions are there. But the basic bottom line is what? Let them go for minimum repulsions. Even in the life also, when you go for minimum quarrel, so more happy, more quarrel and less happiness. Like that, here quarrel is compared to the repulsions. So in a molecule, repulsions are there. In a life, difference of opinions are there. But let us go for the minimum difference of opinion. We will go for the maximum agreement, maximum adjustment, maximum compromisation. Like that, even in the molecular level also, they should go for among the repulsions, let them go for the minimum repulsions so that we can go for the stable compound. That is the bottom line or the crux of this theory, known as what? Valence shell electron pair repulsion theory. The VESCPR theory. This is given by Sidgwick and Powell, most important scientist. This theory is based on repulsive character of electron pairs in the valence shell of atoms. I told already, okay. So in the valence shell, how many electron pairs are there? Let them go for minimum repulsions after the bonding. And these are the scientists who have worked in this field, the VESCPR theory. So for these pictures, I have taken the help of what? Extra marks. So these pictures I have taken to give respect and to see their work what in the field of what? VESCPR theory. So Gillespie, Nelom and Sidgwick. Okay. Now let us understand what are the main postulates of the VESCPR theory. The exact shape of molecule depends upon number of electron pairs around the central atom. How many electron pairs are there around the central atom in a molecule? In that, how many are busy in the bonding? How many are not busy in the bonding? That you have to take into account. The electron pairs tend to repel each other since they exist around the central atom, and the electronic clouds are neutrally charged. Around the central atom, we find electron pairs in the form of electron clouds. So because they are neutrally charged, naturally they want to repel each other. But the problem is what? Let them go for the minimum repulsions. Electron pairs try to take such position which can minimize the repulsion between them. So when they combine, when they go for such a shape where they feel that in this shape we are having minimum repulsions, and that is the most stable. So chemical bonding mantra is what? Least repulsion, most stability. The valence shell is taken as a sphere with the electron pairs placed at distance. So here we have to presume that all electrons are like a sphere around the central metal atom, and in that spherical region, so they will take some shape in 3D in space with keeping some distance between them. However, keeping in the present scenario the social distance, in the same way they also keep some distance so that repulsions are minimum and they're happy. A multiple bond is treated as if it is a single electron pair, and electron pairs which constitute the bond as a single pair. By chance, first single bond is formed. If more number of electrons are available for still bonding possibility is there, then they will let them go for the multiple bond, that is a double bond or the triple bond. But first single bond has to form to give the frame, then they go for the double or triple depend upon the availability of the electron pairs. That too, they go for the sideway attraction, then multiple bond is formed. The maximum repulsion is between lone pair electron and lone pair electron, and the minimum between bond pair electron and the bond pair electron. See, in every molecule there are two pairs of electron. One is a lone pair which is not busy in the bonding, and the other one is what? The electron pair which is busy in the bonding. The pair which is busy in the bonding is called as bond pair, and the pair which is not busy in the bonding is called as non-bond pair or the lone pair. So any molecule which has got more number of lone pair, that means it is having more repulsions, because lone pair is free, no? So when they are free, they do something gadbada. So they want to repel each other. So more the number of lone pair, more are the repulsions. Then to take shape is very difficult. So they will take some shape which is happy for all. So we should ensure that the molecule should have no lone pair, all are bond pair, then that is the most happiest, most stable structure. So among the repulsions, it is the lone pair is the most, and the bond pair is the least. The bond pairs and the lone pairs minimize the repulsion and take the position with minimum repulsion in space, this I told, so that stability is attained. So in conclusion, among the repulsions, it is the lone pair is the maximum, moderate is lone pair, bond pair, last is bond pair, because they are busy in the bonding. They don't repel that much, but here out of two, one is free, so they create problem. Here both are free, maximum repulsion. So molecule should have first priority, this one or this one or this one. So this is last priority. So if it is there, then they have to think what shape you have to take, keeping in mind minimum repulsions. See, these are geometry of molecules in which the central atom has no lone pair. All these are no lone pair, all bond pair, all bond pair. Okay. Examples are what? Beryllium chloride, where no lone pair. In the boron trifluoride, no lone pair. Boron with busy with all three fluoride atom, fluoride ion. So in the same way, methane, okay, with no lone pair. So PCl5 with no lone pair, SF6 with lone pair. So all are bond pairs, they are happy. So they take this shape and they are happy with this shape. So shape is decided by lone pair, bond pair, and the bond pair. Here no lone pair, all happy with this shape. So that's why they have taken this shape in the space. Now these are examples for what? Molecules having lone pair. Bond pairs are, bond has to be there. Along with the bond pair, now lone pairs are there. I told minimum lone pairs, no. But he has given some examples here. One lone pair. So one lone pair, two lone pairs, one lone pair, two lone pairs, one lone pair, two lone pairs. So this is AB2 type with one lone pair, E for one electron pair. AB3, okay, with one lone pair. AB3 with two lone pair. AB4 with one lone pair. So like that, general examples, exact examples are here. Okay, this is SO2. This is S, this is O, O, SO2. Why it is bent? Because this is the lone pair. This was the repulsions are there. It want to straight go for straight, but not possible. So this is going for the repulsion here. So it is bending, like making some angle. Okay. In the same way, one lone pair is going for the repulsions here. So bent structure. So this is what ammonia case trigonal pyramidal name is given, and this is what example water. Here you see two lone pair. So this pair repulse like anything. So this will again one repulsion here. This is repulsion. So this want to pull like this. This want to pull this way. So angle is still lesser than the ammonia. Therefore, this has gone for the very much bent structure water. In the same way, SF4 has gone for the sisa. Keeping in mind this lone pair, only one lone pair. ClF3, okay, ClF3. This is also 1 with 3. Sorry, 1 with 4. This is 1 with 3 only. But here there are two lone pairs. They want to repel each other. So this is the best shape for the ClF3. And for BrFi, Br at the center, and all these are F. Okay, BrFi with one lone pair. Happy with what? Square pyramidal. And for xenon tetrafluoride, okay, two lone pairs are there. So this will take in space one shape. This will take one space. They four occupy the four square. So square one pyramid, other pyramid. So square bipyramidal. Okay, okay. Or this is called what? Octahedral. Or if you don't consider this lone pair, it will take the square planar. So depend upon the number of electrons available. Okay, they will take the geometry. That's why I told in the beginning, this is the molecular geometry. Now please see here, why this has taken bent shape, why this has taken diagonal bipyramidal, bent, seesaw, T shape. This example idea made it clear, and here he has given explanation for the lone pair, bond pair, and the bond pair. So keeping in the mind these three repulsions, and ultimately again I will repeat the mantra of chemical bonding: least repulsions, least energy, maximum stability. So these 3 points are kept in the mind, then they go for proper shape, and is explained. Please go through all these reasons why it has taken the shape. You'll understand. Otherwise, if time permits, we'll discuss in our due classes. Okay. Thank you, my dear students.